Alright, hello class. In this video, we're going to be continuing our discussion on lines and curves in space, but specifically we are going to be looking at how we approach this in 3 dimensions. Okay, so this advice I'm going to show in this particular lecture is how I usually suggest we always approach trying to visualize 3D elements on 2D planes. I'm going to be using software to show you how these things look, but also I want to show how you can just use your own, notes, your own scratch paper to visualize what's going on. Okay, so I find it easiest to just look at an example to start with. So here is a 3-dimensional vector valued function, cosine t, comma sine t, comma t. And, we can let t range as far as we want. I'm going to say let it go from 0 to 4 pi just to get 2 full rotations out of it. But we can extend that later if we want to see more of what's going on. But my first piece of advice is to isolate to a single plane, usually the XY plane. So usually I start by seeing what's happening just on the XY plane, right? So here's my X, here's my Y, and of course, here's my Z in the final component there. But I'm going to start just by looking at this, and here, this XY, that's cosine t comma sine t. So on the XY plane, we have a circle, specifically a circle with radius 1. Okay, so here, this vector valued function, just cosine t sine t, all we're doing is looking at the XY plane, is we have this sort of behavior going on. And if we're going from 0 to 4 pi, we do one rotation, and then we do another rotation. Okay? So, then, what I do is I go through and I start looking at what z does. So z is just t. Okay, so when t is equal to 0, so that's what we'll start with. When t is equal to 0, we're right here on the xy plane, and z is going to be 0. Okay? When t is equal to pi over 4, z is also equal to pi over 4. When t is equal to pi over 2, well, so is z. Okay, and then here z would be pi when t is pi. And so on. Here z would be 3 pi over 2. Then when we get back around to here, we have another step, okay, where z is equal to 2 pi. That's when t is equal to 2 pi. And we have another rotation with z slowly getting larger and larger. In fact, if we were to graph just z by t, well, we would just have this line here. Okay, because as t increases, z increases by the same amount. So what's happening is as this object is spinning around, so if we look at it from the top looking down, all I would see is this. But as that's happening, right, I can think of it this way. We'll have our z increasing if we think of it as it coming out towards us. Okay, so let's take a look at what's going on just in 3 dimensions on a graph. It'd be a lot easier to see what's going on there, and we'll cut to that now. Okay, so to start with, I'm trying to match the colors here, but in pink we have the circle here on the XY plane. Okay, and it, as time goes on, it's just moving around this circle here. Okay, so that's what's going on the XY plane. However, at the same time, we have a path being charted out along Z. So as t increases, Z increases by the same amount. So as that happens, let me play that here, is something like this. Okay, so it's lining up with the circle. Okay, but moving upwards at the same time. So let me maybe get a height line to kind of show what's going on here. All right, here we go. I've put on a height here, and I'm not showing the curve. I'm just showing the point at where it would be, okay, at each particular time. And you can see that it is like spinning around this circle here, and as it's doing so, the height is increasing over time. Okay, and here it is with the curve traced out. Okay, so remember, these things are not actually this whole, well, I mean, it's this curve itself. It's tracing this curve out. However, the vector valued function itself is actually this movement along the path and how it is moving. All right, so now I've set this up with the vector pointing to the point. Okay. So as you can see, just like before, the vector is pointing from the origin to the point that the object is at any given time. All right, and here I think maybe we have a more zoomed out view. Okay, I got it centered a little better this time. And you can actually see, what I like about this software is you can see where it's behind the z-axis and in front of the z-axis. Okay, now, let's drop the vector and the segment there. This object is called a helix, which if we take a look at it, probably makes some sense because, well, it looks sort of like a DNA strand, right? So, but when we look at it from straight above, all we see is the circle. Okay, and then okay, I think it's always best to get a good view at a bunch of different angles to kind of see what's going on. But this is called a helix. It's, the function itself is traveling around the circle, but as it does so, it moves up the helix. All right, let's alter this a little bit and see what we get. All right, for the next function we're going to look at cosine t, comma sine t, then sine squared of 5t. And we're just going to look over one full rotation, but the xy plane is still looking at the same circle. Okay, however, what sine squared of 5t does, well, that oscillates, right? If we start looking at z versus t, sine squared, well, that just makes everything positive, and 5t just makes it oscillate faster than normal sine. So these should be touching 0 here, but what's happening is as t increases, z is oscillating back and forth, bouncing up and down. And so what's going to happen is as the object moves around the circle, it will bounce up and down. So it's going to act kind of like a ball bouncing around a circle. And we can see that on the graph. Okay, I've set up the graph in the same way as before, just with the new function, and we can see that behavior now. The same little pink circle that it's traveling above, but now z is jumping up and down, right? And so as we oscillate around the circle, z oscillates from 1 to 0. Okay, so it almost makes like a little crown looking shape. All right, so when I was recording this originally, this part of the lecture actually got dropped out. So I just wanted to come back real quick and say that the example that we're going to look at now is this one, where w is equal to cosine t, comma sine t, comma e to the negative t. And we're looking at t going from 0 to 4 pi. The thing to note here is that our xy plane, we still have the circle like we've been looking at, and then in our z is e to the negative t, and e to the negative t starts here at 1 and shrinks down to 0 really quickly. Okay, so in the graph that we're going to look at, we're going to see that where the height in z shrinks down to 0 really, really quickly while we're spinning it around the circle. Okay, so we'll jump to the graph now. Okay, so here's the graph. Okay, as we're spinning around, I did drop off the x-axis here just to give a better look of what's going on. But as we can see, we started here with a height of 1, and then as we started spinning around this circle, we get closer and closer to the xy plane, but never actually get there. Okay, but it does seem like we get incredibly close. All right. So you can almost think of this as like a smushed helix, right? We start here, and if we let time go on, it would just continue spinning around over and over and over again here, but would never actually hit the xy plane, which is in gray. Okay, so the couple things I want to show here, because this is basically the idea. You isolate a set of axes, you see what's going on there, and then you take a look at what's happening elsewhere. So it doesn't actually have to be the xy plane that we look at. Here the xy plane is not going to be all that useful to us, but instead, if I notice that we have our typical circle in the xz plane, okay, we can actually think of it in terms of that instead. So here would be the xz plane, and that is making a circle like so, and then it's in the y-axis. So if we think of here as the, whoops, wrong button. If we think of this as the positive y, as we spin around the circle, we start revolving around the y-axis. So this would be a helix spinning out around the y-axis. So I'm just showing this one to show that it doesn't have to be on the xy plane where, say, your circle is or what you're analyzing. It could be any of the planes, and you look at, say, y in this case. So here I'll do the the YT axis, which would literally just be this straight line. Okay, so let's take a look at it on a graph and see what we get. Okay, so here we are on the graph now, and I'm going to start with just the circle that is on the XZ plane. So you see that it is moving just along the XZ plane. Okay, and what I like about it is it kind of hashes it out beneath the XY plane. And now it was in the Y, so the Y going in this positive direction should be where we start to see the helix forming. So let's do that, and there we go. There is the helix. Okay, and we can see that it is just moving along the positive y-axis. Okay, here's a more zoomed out view so we can see what's going on here. And notice the points are always in line with one another. Okay, so this is a helix going out across the y-axis. Now, for the next example I want to look at, I do want to show that it does not have to be over a circle. We can be over anything, a parabola, an ellipse, sine, cosine, whatever. It really, you know, it doesn't, it's not just circles. Circles are important, but you know, it's not the only thing that we're going to look at. So let's look at a couple more examples, and that should pretty much be it for this particular section. Okay, so for example, let's take WT here. W of t is t squared, and sine of t. So in the xy plane, this is going to be a parabola because this is x equals t, y equals t squared. When you plug that in here, you get y is equal to x squared. So when we set this up, since we're only going from 0 to 4 pi, we're going to get the parabola t comma t squared. Okay, but as we go along, the z, on the other hand, is going to be oscillating up and down. And this is not exactly what it's going to look like at all, okay? I'm just kind of trying to give myself an idea of what's happening. So sine of t, we know if we're doing z versus t, we'll get our usual sine wave. But what's happening is I always like to think of it as, imagine you're taking this sine curve, imagine it's on a piece of paper, right, or like a transparency, and you're moving this over to here and lining it up along with this curve here. Okay, and then you're getting a 3D object doing that. Okay, so let's actually take a look at it on the graphing software and see if this little sketch I've put together actually gives me a sense of what's happening. All right, and actually, before I go to graph this, what I'm going to do instead is actually use sine of something crazy like 10t, and then I'm just going to let t go between like 0 and 2, just to get a lot more oscillations in a smaller space. But the idea still, you know, holds up for what I'm trying to do. But we'll see once we get to the graph why that is. All right, to start with, here is just the parabola in pink. Okay, so here's the XY plane. Here's X in red, Y in green, and we can see tracing along the plane itself. Okay, now from here, I'm going to add in the full curve. Okay, and so as we travel along this parabola, the object itself is moving up and down like sine. And so, as I said, I made it sine of 10t just so we'd get a lot more oscillations. Okay, but if I pause it here, we can see that it's essentially sine, but it's just moving along this parabola here. Okay, and the bounding box is a little messed up. Okay, there we go. There's a closer view of what's going on. And you can see here it really is just sine, but it's being deformed along this line. All right, and there are so many different ways we can change this. We could put whatever function we wanted. And in fact, maybe I can go ahead and change this curve to let me square the sine. And you can see now it's bouncing along the top of the parabola. Okay, and again, there are lots of things we could do here. Okay, here I've put the natural log of t into the z-axis. So it's the function natural log, but it's being basically traced along the parabola. Okay, so again, lots and lots of things we could do here. So you can even see we have the vertical asymptote like we normally do, and it starts to increase very slowly, but again, it's adjusted to follow this path. All right, so I think that's probably a good enough place to stop here when it comes to talking about vector-valued functions. It's always, and this advice that we have here regarding how we approach this is how we're going to be approaching a lot of these things, where we see what's going on the XY plane or one of the other planes, and then we see then what is happening in the third axis, usually the Z. All right, so that should probably do it for this particular lecture. I will see you all in the next one. Cheers.